Passage 4. This passage is adapted from the essay Making Stuff from Bacon to Bakelite by Philip Ball. During the Industrial Revolution, the high price of steel meant that many large engineering projects were carried out that used instead cast iron, which is brittle and prone to failure. This was why Henry Bessemer's new process for making steel was greeted with jubilation. The details announced at a meeting of the British Association in 1856 were published in full in the Times. Bessemer himself was lauded not just as an engineer, but as a scientist, being elected a Fellow of the Royal Society in 1879. Bessemer's process controlled the amount of carbon mixed with iron to make steel. That the proportion of carbon governs the hardness was first noted in 1774 by the Swedish metallurgist Torbjörn Bergman, who was by any standards a scientist teaching chemistry, physics, and math at Uppsala. Bergman made an extensive study of the propensity of different chemical elements to combine with one another, a property known as elective affinity, central to the 18th century notion of chemical reactivity. He was a mentor and sponsor of Carl Wilhelm Scheele, the greatest Swedish chemist of the age and co-discoverer of oxygen. Oxygen as a component of air was the key to the Bessemer process. It offered a way of removing impurities from pig iron and adjusting its carbon content during conversion to steel. A blast of air through the molten metal turned impurities such as silicon into light silica slag, a collection of compounds removed from metal in the smelting process, and removed carbon in the form of volatile carbon dioxide. Pig iron contains as much as 4% carbon. Steels have only around 0.3 to 2%. Meanwhile, the heat produced in these reactions with oxygen kept the iron molten without the need for extra fuel. It was long known that steel can be improved with the spice of other elements. A dash of the metal manganese helps to remove oxygen and sulfur from the iron, and most of the manganese currently produced globally is used for this purpose. Manganese also makes steel stronger, while nickel and chromium improve its hardness. And chromium is the key additive in stainless steel. In a proportion of more than about 11%, it makes the metal rust resistant. Most modern steels are therefore alloys blended to give the desired properties. But is this science? Some of the early innovations in steel alloys were chance discoveries, often due to impurities incorporated by accident. In this respect, metallurgy has long retained the air of an artisan craft, akin to the trial and error explorations of dyers, glassmakers, and potters. But the reason for this empiricism is not that the science of metallurgy is trivial, it is because it is so difficult. According to Rodney Cottrell, a remarkable British physicist whose expertise stretched from the sciences of materials to that of the brain, metallurgy is one of our most ancient arts, but is often referred to as one of the youngest sciences. One of the principal difficulties in understanding the behavior of materials such as steel is that this depends on its structure over a wide range of length scales, from the packing of individual atoms to the size and shape of grains, micrometers or even millimeters in size. Science has trouble dealing with such a span of scales. One might regard this difficulty as akin to that in the social sciences, where social behavior is governed by how individuals behave, but also how we interact on the scale of families and neighborhoods within entire cities and at a national level. That's why the social sciences are arguably among the hardest of sciences too. The mechanical properties of metals depend on how flaws in the crystal structure, called defects, move and interact. These defects are produced by almost inevitable imperfections in the regular stacking of atoms in the crystalline material. The most common type of stacking fault is called a dislocation. Metals bend rather than shattering like porcelain because dislocations can shift around and accommodate the deformation. But if dislocations accumulate and get entangled, restricting their ability to move, the metal becomes brittle. This is what happens after repeated deformation, causing the cracking known as metal fatigue. Dislocations can also get trapped at the boundaries between the fine, microscopic grains that divide a metal into mosaics of crystallites. The arrest of dislocations at grain edges means that Metals may be made harder by reducing the size of their grains, a useful trick for modifying their mechanical behavior. The main purpose of the passage is to explain in detail the various experiments Bessemer conducted in order to develop a better steel, provide an overview of some of the scientific principles that apply to the creation and behavior of steel, describe some of the philosophical questions concerning metallurgy, illustrate the differences between pig iron and cast iron. So I think the best answer for this is option B. Large parts of the passage are interested in how steel is produced and why it behaves the way it does. And that discussion then leads into a discussion on metallurgy in general. So B is a good answer. It's not just focused on Bessemer, but talks about much else. So it's not A. It does not look at the philosophical questions metallurgy raised, so not C. And it definitely looks at much more than the difference between pig and cast iron, so B. The author most likely includes details about the initial response to Bessemer's new steel-making process in order to emphasize that Bessemer's new process was a significant achievement for industry, provide support for the author's opinion that Bessemer's new process was prone to failure, describe Bessemer's qualifications as an engineer, provide specific examples of the criticism that Bessemer's new process received. So this is F, right? We know that during the Industrial Revolution, the high price of steel meant that most engineering projects were carried out using cast iron, which is brittle. And so when Bessemer came up with this new process, it was greeted with jubilation. So it was appreciated and celebrated across the industry. 33, it can reasonably be inferred that the author includes the information that Bergman was a mentor and sponsor of Shields mainly to introduce the fact that Bergman was a teacher as well as a scientist, suggest that Bergman was a more successful scientist than Shield was, give an example of the 18th century notion of scientific communities, reinforce Bergman's credibility as a scientist. So we speak about Bergman here, right? The Swedish metallurgist Torbjörn Bergman, who was by any standards a scientist teaching chemistry, physics, and mathematics at Uppsala. And then he made an extensive study of the properties of different chemical elements, and he was a mentor and sponsor of Carl Wilhelm Scheele. So the fact that he was a mentor kind of reinforces his credibility as a scientist. It doesn't introduce the fact that he was a scientist, that's already spoken about, but the fact that he was a mentor reinforces his credibility, so D. According to the passage, which of the following conversions is a direct result of adding oxygen to molten pig iron? Light silica slag is converted into carbon dioxide. Carbon dioxide is converted into carbon. Silicon is converted into light silica slag. Impurities in the metal are converted into silicon. So this is H, right? It comes from here that when you pass a blast of air through the molten metal, it turns silicon into light silica slag. In the context of the passage, the main effect of the word spice is to emphasize that. So spice is here. It was long known that steel can be improved with a spice of other elements, right? So you have a dash of the metal manganese, and then you have chromium, which improves steel's rust resistance, right? So what is the context of using spice? Elements must be gradually mixed into steel in order to produce the desired effect. Adding certain elements to steel can enrich the steel's quality. Manganese, chromium, and nickel are used sparingly in steel because of their expense. Blending elements is a trial and error process that has not yet yielded positive results. So it's B, right? We are talking about adding certain elements like manganese and chromium to enrich the quality of the steel. Based on the passage, which of the following statements would the author most likely agree? Metallurgy is not an art because it requires too much scientific knowledge. Metallurgy is too difficult to be considered a science. Metallurgy is a science as well as an art. Metallurgy is a trivial science. So this is H, right? This comes from here, that because it involved so much of trial and error, metallurgy has long retained the air of an artisan craft. But the reason for this empiricism is that it is a difficult process, right? So it has both elements of art and science. And in fact, the author also quotes Cottrell, who said that it's one of our most ancient arts, but one of our youngest sciences. So both art and science. The passage most strongly suggests that the study of the behavior of materials and the study of the social sciences are similar because they require analysis that span a wide range of scales, are based on trial and error experimentation, involve examination of the size and shape of individual atoms, produce results that must be interpreted by both scientists and artists. So this is A, right? We know that um, the behavior of materials such as steel is that it depends on the structure over a wide range of scales. And in societies also, in social sciences, the behavior is governed by how individuals behave with one another, but also on the scale of families, neighborhoods, cities, and nations. So it's a matter of scale. The main idea of the last paragraph is that, so the last paragraph talks about the defects in metal structures and how those defects, such as dislocation, cause certain properties in metals, right? For example, if dislocations accumulate and get entangled, the metal becomes brittle. And they also kind of look at what can be done to remove these dislocations or lessen their impact. So the arrest of dislocations at grain edges means that metals may be made harder by reducing the size of their grains. So this is kind of looking at the defects and how to address them. Defects in the crystal structure of a metal determine that metal's mechanical properties. Dislocations are the most common type of stacking fault in a metal. The mechanical behavior of a metal can be modified by increasing the size of a metal's grains. Microscopic grains divide a metal into mosaics of crystallites. So let's first eliminate G and J because they are quite specific. Between F and H, let's just see which is better. Defects in the crystal structure determine that metal's mechanical properties. How flaws in the crystal structure move and interact. Yeah, that is a good option. What about H? The mechanical behavior of a metal can be modified by increasing the size of a metal's grains. Okay. Okay, so the arrest of dislocations at grain edges means that metals may be made harder by reducing the size of their grains, a useful trick for modifying their mechanical behavior. Oh, reducing the size, not increasing. So this is actually inaccurate. So F. As used in line 56, the word stretched most nearly means 56. A remarkable British physicist whose expertise stretched from the sciences of materials to that of the brain. So ranged from, right? So it strained, exaggerated, extended, and amplified. So extended, right? It went from one discipline to another discipline. A strain is used in the negative context of something being under strain. That is something which is tense, so it's not A. Exaggerate is also used in a negative context when something is exaggerated, more weight is given to it than is needed, so not this. And amplified is when you kind of, for example, to amplify an opinion, which is to kind of, make sure that it reaches more people than it currently is reaching, right? So again, that doesn't fit the context. We are looking at ranging from one discipline to another, so extended. According to the passage, reducing the size of a metal's grain can make the metal, it can make the metal harder, right? Because that's what we are saying here, that metals may be made harder by reducing the size of their grains. So it's J. Okay, let's grade this. BFDHB BFDHB, 36 HAFCJ, HAFCJ. Okay, great. So we got all correct. With this video, we have completed the solutions to all sections of the July 2020 ACT Form C01. I'll link to those in the description box, so do check those solutions out. I'll see you guys in a new video soon. Take care. Bye-bye.